Okay, finally we arrive at the most um, important section of thermodynamics in terms of points on the AP test in May, and that's PV diagrams. So this is going to be related to um, everything we should know about Pipnert, the ideal gas law, but it's also related to internal energy being given as 3 has nRT. And it's also related to understanding when work is being done to or by a gas, and whether heat is going into or out of a gas. And you need to know the different processes: the isobaric, the isothermal, the adiabatic, and the isovolumetric, or sometimes it's called isochoric. So here we're looking at a PV diagram. Notice P along the vertical axis and V along the horizontal axis. More than that, look at the red curve. Notice how um, the curve's kind of going upward to the left on a kind of an inverse or hyperbolic path. So it's going from a low pressure and a high volume VI to a high pressure PF and a small volume VF. The working accomplished in a process is the area under the curve on a PV diagram. So notice how it's kind of a yellowish color here. All that area underneath the curve is the working that's being done. In this case, the volume's decreasing, so that means it's being compressed, which means work is being done to the gas. So for the first law of thermodynamics, that's the change in internal energy equals Q plus W. In this case, W is going to be positive because the work's being done to the gas. This amount of work done, since it's the area underneath the curve, is dependent upon the path taken. In this case, energy is being transferred by working from the environment to the gas because it's being compressed. By the way, that red line, that's an isothermal process. Isothermal means constant temperature. Everywhere on that red line, from initial to final, is a constant pressure, or excuse me, constant temperature. So here we have three different processes. They all start at the same initial and they all have the same final states. But notice the area underneath the curve is different. It's the most in B and it's the least in A and C somewhere in the middle. So there's different amounts of working being done. By the way, the name of the processes are shown here. The horizontal lines are called isobaric. That's because they are at a constant pressure. The inverse line you can see on the far right, that's the isothermal we already talked about. The vertical lines, where the volume is constant, is called isochoric. Sometimes it's called isometric. Sometimes it's called isovolumetric. The working done differs in each process. The working done depends upon the path. So for every one of these, notice what's happening. It's going from high initial volume to a lower, smaller volume. Even in C, it's going from a very high volume along the horizontal axis to a very small volume. In other words, the gas is being compressed. If it's being compressed, that means work is being done to the gas. So in the first law, change in internal energy equals Q plus W. W is going to be positive in these cases. So these are going to be the three equations that are going to be very important in this unit. Change in internal energy is going to be equal to Q plus W. That's the first law of thermodynamics. That's conservation of energy. The change in internal energy is given by 3 has nR delta T. That's for a monatomic gas, which is what you'll see on the AP test. The reason it's 3 is because there's 3 degrees of freedom. Could be moving the X, the Y, or the Z direction those particles could be. And of course, then we have the ideal gas law, Pibnert. So look at the PV diagram we have here. notice we have a gas that goes from A to B to C to D to back up to A again. When it goes from A to B, notice that temperature T3 is constant. That's an isothermal, process. Then when it goes from B to C, it goes from one isotherm to another isotherm. That is an adiabatic process. And then when it goes from C to D, that's at a constant pressure. That's an isobaric process. And then finally, when it goes from D back up to A, the volume doesn't change. That's an isometric or isochoric process. There's some things that you need to know about these different processes. Of course, if it's isothermal, like number 1, there's no change in temperature. So therefore, the change in internal energy is going to be 0. Whenever you have an isothermal process, change in internal energy is 0. So if you're thinking the first law of thermodynamics, over here, this will be 0. For adiabatic processes, like B to C, they happen so quickly, or they are immersed in some kind of insulator, that heat cannot move into or out of the system. So whenever it's adiabatic process, there is no heat. Q will be 0. And then lastly, the isovolumetric or isochoric process, this number 4. Remember we said that work is the area underneath the curve. Well, there's no area under the curve for number 4 here. It's a vertical line. So whenever you have an isochoric, isovolumetric process, when the volume's constant, the work will be 0. In number 3, though, the work is not 0 here. There is area underneath this line. It's just not shaded in. Okay, so let's go ahead and continue with this one. Process 1, isothermal, delta T is equal to 0. Integrating along the inverse curve to find work gives, now of course if you're a big exam person, you don't need to know how to integrate along this, but if you did integrate, this is the equation you get. So just in case you're wondering where this equation comes from, and yes, this is one you need to know, it comes from integration process. So integrating along this hyperbolic or inverse curve gives us the work is equal to nRT times the natural log of the final volume divided by the initial volume. And in this case, where it goes from a small volume to a higher volume, this will be a ratio bigger than 1, so natural log of that will be a positive number. So the work in this case is going to be positive. Notice the gas is expanding. So if the gas is expanding, is work being done to it, or is it being done to the environment? Hopefully you said it's being done to the environment. In that case, would you use a positive or a negative then in the first law of thermodynamics? Well, whenever work is done to the environment, that means energy is leaving the system being the gas. And so we would actually use the negative here. So even though when you do this you end up getting a positive, you have to put it as negative in this equation. Tricky. You have to be careful about that. That's where students make mistakes. So here we have the first law of thermodynamics. We're going to plug in the negative. And don't forget, this was an isothermal process, so there's no change in internal energy. So that would be 0. And that means the heat that was into the system would be the same as the amount of work that went out of the system. So here we have heat coming in across this line into the gas, and we have work, and I call it W1, that's leaving the gas, same amount. Okay, let's look at the next process. It's an adiabatic, number 2. And in this case, when it's adiabatic, the heat would be 0, Q would be 0. Happens so quickly or it's insulated. So we start with the first law of thermodynamics. 0 is the amount of heat, so the change in internal energy would be equal to W. Change in internal energy is given to 3 has nR delta T. And so in this case, since delta T is negative, it goes from a high temperature T3 to a lower temperature T2, there's going to be work that's leaving the system. So W is going to end up being negative. That means work's leaving the system. And again, we can see that because notice it goes from this volume to a bigger volume. So again, it's expanding and it's going to be doing work to the environment. Okay, so let's look at process 3. That's the isobaric process. And in that case, the change in pressure would be 0. In this case, the calculated work P delta V, so the area underneath this, we have a constant pressure, the change in volume. It goes from this high volume to this low volume. This amount of work is going to be negative. So it's going from a high volume to a small volume. It's contracting. The gas contracts. So would the W that we put in, what would it be? Would it be positive or negative? When we calculate it, we get negative. Yes, we turn in positive. Why? Well, because W is defined as the work done to the gas. Okay. Well, this amount of work right here is the work done by the gas. We want the work done to the gas. It's contracting. It's going from a big volume to a small volume. There's being work done to it. So the amount of work done to it is going to be the opposite of this. So plug in what delta change in internal energy is. Plug in what the work is, which is negative P delta V. And rearrange this. And we figure out what the Q is equal to. And temperature 1 is going to be less than temperature 2, so this term is going to be negative. Volume at D is going to be less than volume at C, so that term is going to be negative. So that means the heat will be negative. So that means the gas is actually losing energy from heat. And we've got work coming into the system as it contracts. Okay, now let's look at process 4. Process 4 is isochoric, so the work is 0. And so that means the change in internal energy is going to be equal to Q. Change in internal energy is 3 has nRT. And T3 is going to be greater than T1, so there's going to be heat coming into the system. For the cyclical process, A, B, C, D, A, the change in internal energy will be 0. So again, it starts here and it ends here. Well, it's the same temperature, so the change in internal energy is 0, which means the work would be equal to negative heat. So whatever heat you put into the system is how much work you're going to get out of the system. For the cyclical process, A, B, C, D, A, so A, B, C, D, the change in internal energy is 0, and so I must have backed up. In this particular process, as the gas expands from A to B and then C, it does a lot of work to the environment. So the gas has a net positive heating and a net negative working. Thus its change in energy is 0. So it does work to the environment. We can see that W1, I didn't label this one, I should have called this W2. And that's going to be greater than this W3 coming into it. So there's a net work going out and there's a net heat coming in. And the total change in energy is 0 because those two heats coming in equal, those two heats coming in minus the heat going out will be equal to the works going out minus the work coming in. Okay, let's say we reverse the process now. Notice how the arrows now are pointing the other direction. They're going around the opposite direction. In this case, what happens is it reverses the heats. So now we have heat flowing out here, heat flowing out here, heat flowing in here. And the works are also reversed now. And so we still get the same relationship because the change in internal energy is 0. Okay, let's look at one more example with PV diagrams. We have 1 mole of a monatomic gas going through a cyclic process A, B, C, D, and then back up to A, where A is at STP. STP stands for standard temperature and pressure. That would be a temperature of 273 Kelvin and a pressure of 1 atmosphere in pascals, so 1.013 times 10 to the 5th pascals. So that's the conditions at A. So let's find the absolute temperature, pressure, and volume at each of these points, A, B, C, and D. That's the first step here. What temperature for A we know is 273 Kelvin, and we know the pressure is 1 atmosphere, or 1.013 times 10 to the 5th pascals. We can use PIVNERT, PV equals nRT, to solve for the volume. So we have a pressure of 1.013 times 10 to the 5th times the volume is equal to N, which is 1 mole, times R, which is 8.31, times the temperature of 273. Solve this, we get a volume of 0.0224 cubic meters. Moving from A to B, that's an isobaric process, so the pressure is going to be the same. We can also see that the volume went down exactly half. It went from this reading to this reading, where this is 0 over here. So the volume is going to be 0.0112. We can use PIVNERT again, or the combined gas law, to figure out the temperature. And the temperature is 136.5 Kelvin. Then going from B to C, the volume stays the same. So the volume will be 0.0112. But the pressure decreases by a factor of 1, 2, 3, 4, 5. So the pressure is going to be 1/5, or 20,260 pascals. Again, we can use PIVNERT with the pressure of 20,260 pascals, the volume of 0.0112. The number of moles is 1. Universal gas constant of 8.31, and solve for the temperature, and we get 27.3. Going from C to D, the pressure stays the same, so it's going to be 20,260 pascals. The volume increases by a factor of, let's see, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the volume is going to be 10 times as much, or 0.112. We can then solve for the temperature using combined gas law. If the volume increases by a factor of 10, the temperature increases by a factor of 10, so we're at 273 Kelvin. So both D and A is at 273 Kelvin. So that process, AD, that must be an isothermal process. Remember, for isothermal processes, the change in internal energy is 0. And for isochoric processes, that's B to C, there's no work because there's no area underneath that line, so the work is 0. Okay, so now we're going to use this information that we just found and figure out what the change in internal energy is, the heat, and the work for each of these processes. So from A to B, I can calculate how much work there would be by taking pressure, which is given as 1.013 times 10 to the 5th pascals, times the change in volume. The final volume is going to be 0.0112, and the initial volume is 0.0224. When you solve for this, you end up getting negative work. So keep in mind that that is the work that the gas is doing. It's negative. So how much work is done to the gas is going to be positive. Look, you're going from A, which is at a high volume, to a lower volume. It's contracting. How is it contracting? There must be an external force pushing it down into a smaller volume. So there's being positive work done to it. Even though the calculation you'll get negative, you put it in as positive. And I get 1135 joules approximately. I can also figure out the change in internal energy by using 3 has nRT. Reason again this is 3 has is there's 3 degrees of freedom that these particles can move in, either X, Y, or Z direction. Plug in the number of moles, which is 1, universal gas constant 8.31, and the change in temperature of going from 273 to 136.5, that's going to give me a negative change in temperature, which gives me a negative change in internal energy. Then I can use the first law of thermodynamics, which is really conservation of energy, to figure out the heat, which is negative 2836 joules. So that means heat is actually leaving the gas. Okay, then going from B to C, there is no area underneath the line. This is an isochoric process, so that means the work is 0. The change in internal energy is going to be given by 3 has nR delta T. Number of moles is 1, R is 8.31. The change in temperature would be 27.3 minus 136.5. Again, it's a negative change in temperature, which means it's a negative change in internal energy. Use the first law of thermodynamics, conservation of energy, solve for heat, and I get negative 1361 joules leaving the system. So it's cooling down. Okay, then from C to D, I can figure out what the work is in this case. Notice it's expanding from a very small volume to a very large volume. It's going to have to do work on the environment. So I'm going to use the pressure, which is given as 20,260 times the change in volume, which is 0.112 minus 0.0112. So when I do this, I'm going to end up getting a positive value because the gas is doing work to the environment. Realize that the first law of thermodynamics, W is defined as the amount of work done to the gas. So if the gas is doing work to the environment of a positive amount, the amount of work that's done to the gas is going to be negative. So even though I calculate a positive number, I plug in a negative and I get negative 2042 joules. I can figure out the change in internal energy by doing 3 has nR delta T. The final temperature is 273, the initial temperature is 27.3, and I get a positive amount of 3062 joules. Use the first law of thermodynamics, conservation of energy, solve for heat, and I get 5104 joules is going into it in terms of heat. Okay, then the process from D to A, I know the change in temperature is 0, so that means the change in internal energy is 0. I can figure out the amount of work done by doing nRT times natural log of VF minus VI. The final volume is this very small amount here at A, 0.0224. The initial volume is 0.112. So when I do natural log of 0.0224 over 0.112, I end up getting a negative. Notice it's going from a big volume to a small volume. It's contracting. There must be an external force doing work here. So even though the gas is doing negative work, there's positive work done to the gas. So I get a negative value, but I put it in as positive into my first law here in a few moments. So now I can solve for Q, and I get negative 3,651 joules. So there's heat leaving in these three processes and heat entering in this one process. Now let's figure out the change in internal energy for the entire cyclic process. I would add up all the changes in internal energy and I get 0. It better be 0 because I return to my initial conditions, so the change in temperature is 0. Let's add up all the work. So I add up all these to figure out the work done, and I get a positive 2,744 approximately joules. By the first law of thermodynamics, conservation of energy, if the gas is doing positive amount of work, or excuse me, if the gas gets work done to it by the environment, then that means that there must be heat leaving the system. So the environment's doing work to the gas. It's compressing the gas. And what happens is that energy is leaving the system, leaving the gas in terms of heat.